So Florence, Durret will be talking about intracluster light with UNIONS in a sample of 200 clusters.
Good morning, good afternoon, good evening, everybody. I hope I first want to thank the organizers for this great meeting. It's been extremely interesting, in particular the community discussions. And I'm going to present these results, which are not completely finished, but they should be presented in reality by Amael Elian, who did a good part of the work, as you'll see. But this has also been in collaboration with Aline Chu, and it's based on UNIONS CFHT data for a sample of 200 clusters. It's clusters of galaxies, not clusters of stars, because we've been hearing all kinds of things. So this time I'm going to talk about clusters of galaxies, and I'll just say clusters. And intracluster light, which I will call ICL. I don't like acronyms very much, but it's just to speak faster. ICL is made of stars, for those who don't know, which are not linked to a particular galaxy. So they're floating somewhere in the usually around the brightest cluster galaxy, and it's believed that ICL contains information on the cluster formation and its evolution, because we have to understand how these floating stars have been stripped or from another galaxy, or how they have been formed. So it was considered until very recently to be a good tracer of dark matter in clusters, but there has been a recent paper by Butler saying that based on simulations, it seems that there's a bias there, so the tracer of dark matter is not as good as we believed. But we're interested in ICL anyway. The problem is that it's faint, it's difficult to detect, so the samples are still limited in numbers of clusters and in redshift. And it's also very difficult to disentangle it from the brightest cluster galaxy, which in some cases I will write BCG. So for those who don't know, it's the brightest cluster galaxy. So all this makes the study of intracluster light difficult. So the two samples of clusters that we've been using were the Kluge sample from Kluge 2020, which is a naval cluster sample of 170 objects with redshift smaller than 0.1. And then to that, we wanted to add more distant clusters. So we added the SDSS RedMapper sample, which has 1,189 clusters, among which 456 are observed in the X-ray cluster survey by Giles. So they have X-ray data, and you'll see in a minute why we need X-ray data to derive cluster masses. So that second sample has redshifts between 0.1 and 0.6. And the data that we have been using is the UNIONS CFHT database in the R-band. So that's CFHT megacam images, which were treated specially by the Elixir LSB. LSB stands for Low Surface Brightness software that was developed by Jean-Charles Cuillandre. So we'll call them RLSB images. So out of all those clusters, we came up with 44 clusters that have RLSB images and 204 clusters from the SDSS sample, among which 86 have X-ray data. So here you have the histogram of the redshift histogram for the complete sample for the two samples. So you can see that at between 0.1 and 0.3 we don't have that many clusters. But it's altogether almost 200 clusters, about 200 clusters, which is nice. We tried to avoid strong galactic extinction, because when we studied ICL in the Perseus cluster from Euclid data, we realized that galactic Sirius could be really terrible to detect ICL. Fortunately, the clusters that we'll be analyzing are more or less in Sirius-free regions, except for a few, so it's not going to be a big problem. This is the Planck dust map, emission map, and the two samples that we have are shown here. So when necessary, we had to assemble 2, 3, or 4 RLSB images because the cluster didn't always fall in the middle of an image. That would be too easy. And then we cropped the resulting image to 1 by 1 megaparsec. And we analyzed and reconstructed the image with a software called DEWIS. DEWIS was developed by Amael Elia during his PhD, which was defended in 2020, so that's already 5 years ago. It stands for Detection Algorithm with Wavelets for Intracluster Studies, and you can find the whole description of the software in Elia and et al. Paper of 2021. So if this is interesting for Sébastien Vincent, who was talking about wavelets. He can get in touch with me, and I will give him Amael Elian's email because he may be interested in testing DEWIS. DEWIS is not very user-friendly yet, but it will become user-friendly sometime. So this is a little video just to show how it works. So you have on the left the residuals. So at the beginning, of course, the residuals are very large, and then in the middle you have the reconstructed image. So you see the objects that are appearing. The small objects are reconstructed before the large ones. So it starts with the little objects, and then you see objects appearing and residuals disappearing, and at the end you find the intracluster light, which is detected, the light detected at a very large scale. I can't show it again because it takes too long. If you want to see it again, just ask me after, if there's time. So DEWIS gives results. Here you have results for 3 clusters. So each line is a cluster, and each column shows. The original image on the left, the restored image in the middle. So you can check that they look pretty much the same. And on the right, you have the cluster model, that is the sum of the intracluster light plus the brightest cluster galaxy plus the galaxies of the cluster. And the dashed circles show a radius of 250 kiloparsecs, just to guide the eye. You can see that, of course, they are not all at the same redshift and they're not all the same size. So our aim was to estimate fractions. So ICL plus BCG fractions, because as I told you, it's very difficult to extract the BCG. So in some case, we tried to do both. So for this, we measure the fluxes within a 500 kiloparsec radius with a limit, or in a surface brightness limit of 26 magnitudes per arcsecond square. That's in that isophote. So the fraction of ICL plus BCG, which is a lowercase f, is the ratio of the flux contained in the ICL plus BCG, which is directly given by DEWIS, divided by the flux of the ICL plus BCG plus what we call the satellites. The satellites are the fluxes of the 10 brightest galaxies with a spectroscopic redshift in the cluster. So we had to eliminate some clusters that did not have 10 spectroscopic redshifts. And we're also testing now, but I don't have the results yet, what happens if we, instead of taking the 10 brightest galaxies, we take the 15 brightest or the 20 brightest. But in that case, we don't always have spectroscopic redshifts for everybody. So here you have a plot of a histogram of the fraction of ICL plus BCG, which is in yellow. And the blue histogram is, in fact, the difference. It's supposed to show more or less the ICL fraction alone, just the ICL. It's the difference of the fluxes in the 26 magnitude per arcsecond square minus the flux in the 25 magnitudes per arcsecond square. So it's like an annulus around the BCG, which is supposed more or less to correspond to the ICL, but it's approximate. We were hoping to find correlations with various quantities. So here we have the ICL fraction as a function of absolute magnitude. So the the colors are still the same. There's a very weak correlation with a Spearman parameter of 0.511. Above 0.5, it's a weak correlation. I can't say I'm sure about anything here. With the eye, I don't see a correlation at all. So that's why we're trying to refine now our definition of the ICL fraction. Then we tried to find a correlation with the cluster mass. So for this, we must estimate cluster masses. So for SDSS clusters, it's quite easy because we correlated our cluster catalog with the XCS survey, which is based on XMM Newton data, and that gives us the X-ray luminosity. And then we apply a scaling relation to obtain the mass, cluster mass, as a function of the X-ray luminosity. So this is the mass histogram that we obtain for SDSS clusters. So except for a single cluster, which is extremely massive, the others are more or less distributed you have a lot of clusters that are not extremely massive. For the Kluge clusters, we haven't finished computing the masses yet, because I must confess that the fluxes that we found were a bit too low. So the masses we find are too low, so I don't want to show them because they may be wrong. And then we looked also, so the ICL fraction as a function of cluster mass for the SDSS clusters give no significant correlation. So here again, it's a bit disappointing. And for those, the same ones which have X-ray data, they also have an X-ray gas temperature. We tried to look at a possible correlation with the X-ray gas temperature, and we didn't find any, so too bad. And finally, we also looked for a correlation between the ICL fraction as a function of and redshift. But if we look at the ICL apparent magnitude as a function of redshift, we get the correlation, of course, that is on the top. But if we compute now the absolute magnitude, we can see that there's a bias, and we're only detecting at redshifts larger than 0.15, we only detect bright objects. So there's certainly a bias there, and we can't say anything about the correlation as a function of redshift. So, of course, what are our perspectives? Well, first, we want to finish our analysis and improve it, if possible. There's going to be an analysis of a morphological analysis of all the ICL and BCG that we have found. Increasing the sky coverage will, of course, increase the number of clusters. And as said on Monday by Jean-Charles and Alan, UNIONS is a partner of Euclid, so there's of course, a big continuation here. And just to finish, I will leave you with this. This is the papers that we have collaborated on Euclid concerning intracluster light. So there's one on the Euclid preparation forecasting detection limits. So Euclid should be able to measure the presence of ICL in 80,000 clusters. So there's going to be a lot of work there because DEWIS is not adapted for such high numbers. There was a study of the Perseus cluster, and there was a study of Abel 2390. But I see I have already spoken 14 minutes, so I should stop here. Thank you very much to the Hawaiian people, to the CFHT staff, to CADC, and to UNIONS. Mahalo.
Are there any questions online? Sorry, I can't see online at the moment. So what do you conclude from the fact that sort of irrespective of mass, etc., the intracluster light fraction is basically a constant? What's your conclusion from that?
Well, we're very unhappy because that's not what we expected. We thought that, the more massive clusters would have more ICL. I think it's linked to the way ICL is created, and it's not in largest clusters that you find more ICL. So ICL must be stripped from the brightest cluster galaxy, but more or less the brightest cluster galaxies are pretty homogeneous populations. So maybe it's just that stars are stripped from the BCG, and the overall cluster mass doesn't matter so much. That's my understanding for now.
Okay. No, great. Thank you very much. We need to move on, so let's thank Florence again.